Hey, what's going on here? Right. Okay. So this is the first of 3 lectures on conformal field theory and combinatorics. Here's the plan of today's talk. So there's going to be an introduction about how the 3 lectures are going to be set up. Then I'm going to tell you something about field theory, about operators, and about modular invariance. So we'll see all of that. So this is the general overview. So today I aim at trying to tell you about some basic concepts of conformal field theory. Tomorrow is going to be dedicated to the so-called Coulomb gas construction, which I'll apply to models of loops living on lattices. So that's already statistical physics models. And then in the third part on Friday, I'm going to give some more specialized applications to combinatorics. So the fact that I need to go all the way to find some applications which might be of potential interest to you means that I'll have to go at a certain pace during the first part of the talk. So I've limited myself to dealing exclusively with 2 dimensions, and there are very good reasons for that. You can investigate what conformal invariance means in other dimensions, but basically it's only a very strong tool in 2 dimensions. So of course the introduction is going to be pretty short because the time is limited. So I'll try to give you some key arguments, but I think that nowhere am I going to give you anything like detailed proofs in a mathematical sense. So most of what I'm going to present has been first derived by physicists, and much of it has later been attacked by mathematicians and has been made much more rigorous. There is one thing that I should mention in particular, that is stochastic Löwner evolution. So many of the results which have been derived by conformal field theory and Coulomb gas methods have now been proven using stochastic Löwner evolution. That is very interesting. However, I'm not going to touch upon that because that would take me too far afield. Also, I should apologize for being a physicist. I see that I'm certainly in the minority here. So I'm going to present things, in a physicist kind of way. So before really taking off, maybe some historical remarks are in order. It's almost impossible to give due credit to everybody who has been implied in this field. So here are just few names. So using quantum field theory in statistical mechanics goes way back, and essentially, if you read Onsager's 1944 solution of the Ising model with your modern glasses, you'll see that somehow he was applying quantum field theory in some sense. But the thing started really gaining momentum with Wilson in '69. He was the guy who invented the idea of renormalization. That is to say that you should see a given system on different scales and try to infer what is going on. That led to the so-called epsilon expansion. There was some crucial input coming from elsewhere. So people who were doing integrability, mainly Leib and Baxter, managed to solve 2 very important models known as the 6 and 8 vertex model. And so they become kind of laboratories where you could see if things that you derived using field theory were correct. So the first important contribution really on conformal invariance was made by Polyakov back in 1970. So he asked the question, what happens if instead of just using scale invariance that, like Wilson did, what happens if you apply global conformal invariance in d dimensions. I'm going to review his results shortly. But the real breakthrough happened starting from 1984, when these three people, Belavin, Polyakov, and Samolodchikov, came out with a seminal paper where they showed that what one should do in two spatial dimensions was not to use global conformal invariance, but local conformal invariance. And that led to a whole range of applications to statistical mechanics. So some of the protagonists are listed here. And it also led to a lot of generalizations. So there is something called extended conformal field theory initiated by Samolodchikov, boundary conformal field theory initiated basically by Cardy. There are important classification issues of rational conformal field theories. And then alongside, there's this other approach to the Coulomb gas, which will be the object of the subject of tomorrow's talk, whose history can be traced back to the late 70s actually, and which was sort of married with conformal field theory in this paper by Di Francesco, Seller, and Zuber from 1987. So let's look on what global conformal invariance means. I should also remark that you don't need to take notes if you don't want to, because the transparencies are going to be made public. So what is a conformal transformation in d dimensions? Well, it's an invertible mapping, say from x to x prime, such that the metric tensor transforms like this, so it's multiplied by some, say, smooth function which depends on space. So basically, what does this mean? So in the renormalization group, the thing was to make these block spin transformations to try to regroup degrees of freedom so that the system would be compressed with a given scale factor. And here we just allow that scale factor to depend slowly on space. So that seems a very reasonable thing to do if we start out with a model which has short-range interactions. So I mean, what would the model care if I tried to renormalize it with a factor of 2 here, and then if I go far away, I renormalize it by a factor of 3? Maybe that would still be a symmetry. So it's a two-line proof to show that this mapping is angle preserving. And you can also convince yourself that it's generated by translations, dilatations, rotations, and inversions with respect to the origin. And so it's actually isomorphic to the group SO D plus 1, 1. And so what the important remark here is the number of real parameters which are in there. So that's 1/2 D plus 1, D plus 2, you can convince yourself. In the whole lecture, I'm going to use extensively that there is a connection between quantum field theory and statistical mechanics. That, of course, has already been touched upon by a number of speakers. So the idea is that the partition function Z is some integral over exponential minus the energy. And so the energy is traditionally called the action here, and it's denoted S. So that's physics. But you can just think of it as some energy. And so the phi which appears in here is all the degrees of freedom of your system. So you can think of Ising spins if you want, but so in general this is some functional, and so there is some functional integration over all the degrees of freedom coming in here. And so the physical observables are going to be correlation functions, right? So correlation functions of various observables, phi1 up to phi k, evaluated at various points in space. And I want to take the average value of that, so it is given by the same functional integral with these factors inserted and normalized by 1 over z. Here comes a small definition. So I want to define something phi as a quasi-primary field, provided that it transforms covariantly. That is to say that phi of x becomes, after a conformal transformation, becomes phi prime of x prime, which is related to the original field just by this Jacobian here to the power minus some exponent delta. And it's one of my goals to derive what that exponent might be, divided by d, where d is the spatial dimension. So delta is a property of the field phi, and it's referred to as its scaling dimension, or critical exponent if you want. So now it's a fact, and it's the main result of this Polyakov 1970 paper, that global conformal invariance fixes the form of 2 and 3 point functions. So suppose that I have 2 points, xi and xj, then I said xij equal to the distance between those. Well, then Polyakov was able to show that the 2 point function is just given by 1 over the distance to twice the conformal, the scaling dimension, provided that these two fields here share the same scaling dimension. If they don't, then it's simply going to be 0. So that's already an interesting result. And moreover, he was able to prove that 3 point functions are also almost fixed by global conformal invariance. So they have these spatial dependencies on all the parameters. And so here, delta 1, delta 2, delta 3 are not required to be equal. And there is some constant here, some constant which depends on the fields 1, 2, and 3. And those constants have to be fixed by some other considerations. I'm going to come back to that.
Excuse me, do those constants depend only on the scaling dimensions of the fields?
They depend on, it's not enough to know the scaling dimensions to say what they are, but they depend on the fields in some way which we can find out later on. Sorry, yes?
The first line, when you say it transforms covariantly, I guess it's at the level of the correlation function. It's not just one random sample field which transforms like that.
Yeah, you're right that most of what I say, I guess almost everything that I say makes sense only when you take correlation functions of the fields.
You take all possible correlation functions and then
right.
transform according to this pattern.
Right, so it's kind of a shorthand notation to write something like this. What I really mean is that if you insert that in a correlation function, then it's true. Starting from 4 point functions, something more interesting is going on, and I'm going to tell you everything about that as well. So they are not fixed just by global conformal invariance. Okay, so that was what global conformal invariance tells us. So let us now go specifically to 2 dimensions, and let's start looking into what local conformal invariance might be. So in 2 dimensions, from the very definition of a conformal transformation, you can see that it means that the Cauchy-Riemann equations are satisfied. So one thing to convince yourself is that I told you that conformal transformations are angle preserving. So that is what Cauchy-Riemann is about. So it's natural to trade the two components of a point in space, x1 and x2, for complex coordinates. So I'm going to define z as x plus I times y, if you wish, and z bar as this thing. And with this definition, a conformal mapping is simply an analytic map. So z becomes w of z. Any analytic function w will do. So the global conformal transformations are supposed, if you believe what I showed you 3 transparencies ago, are supposed to have 6 real parameters. So they take the form of projective transformations like this. So that's something which is well known from electrostatics and things like that. Engineers use such transformations a lot. So the A are complex numbers, and the determinant of the A's is 1, so there are 6 real parameters. So now what is this thing here about analytic maps? Well, analytic maps in some sense are only conformal locally, because they don't need to be defined everywhere. They don't need to be free of singularities. But it seems natural, since we want to work with something which comes from theories with local interactions, that we should relax this constraint that the transformation should be conformal globally, and say that it should only be conformal locally. And with this relaxation, we have at our disposal an infinity of parameters, not only 6, because an analytic function is defined through its Taylor expansion. And so you can see that there's one generator for each power of z. Right. So let me move to my new notation, my new complex notation. Well then, the transformation law that I showed you before is going to look like this. A field, a quasi-primary field transforms like this. So there's this dw dz to the power minus h, and then dw bar dz bar minus h bar. And so now I can define what a primary field is. So a quasi-primary field, or some field that satisfies this for projective maps. And a primary field phi satisfies this for any analytic map. So clearly, if you have a primary field, then it's certainly quasi-primary, but the opposite is not true. So there's a little bit of nomenclature which goes with this. So now the real parameters h and h bar are called the conformal weights, and their sum is called the scaling dimension, and their difference is called the spin. And the spin, of course, is not the same thing as a spin in the Ising model. It's just some other name, right? So, at the very core of conformal field theory is an object called the stress tensor. And the stress tensor enters in some identities which are called the Ward identities. And these are kind of instrumental for deriving my point 3, which will come down here later, the operator formalism, and making links with algebra. So here is the definition of the stress energy tensor. So I have already defined what the partition function is, and here's the metric. So the functional derivative of log of the partition function with respect to the metric defines this stress energy tensor. So what does that mean? Well, it means that the stress energy tensor is the response of the system to anisotropy. And so some of you might know the theory of integrable systems. So in integrable systems, one does more or less the same kind of thing when you define the transfer matrix of a system as the response. Sorry, when you define the Hamiltonian of the system as the response of the transfer matrix with respect to anisotropy. So there is some kind of analogy here, right? So now, using conformal transformations of various types, I can derive some properties of this stress energy tensor. And so now it's interesting for us to trade these indices for, to go to the complex notation. So instead of working with Cartesian conventions for these indices here, I'm going to move to this z bar notation. And then I'm also going to use the metric tensor to bring these indices here downstairs instead of upstairs. So if I do that, and if I use translational and rotational invariance, I find that tz z bar and tz bar z is equal to 0. If I use that and also scale invariance, I find that the derivative of tz z with respect to z bar is equal to dz tz bar equal to 0, typo. So this is, those two here are equal to 0. And so that means that if I now invent another name for tzz, I call it just t of z, well, then that is actually an analytic function.
What does putting a subscript z mean?
Well, t here, is defined in this way, okay.
Those are superscripts.
And so those are superscripts, okay. So if I want to pull them downstairs,
You're
then
pulling it down with a metric tensor.
Right.
Okay. Just want to know what your convention was. A lot of people in applied mathematics would use that for partial derivatives. So,
oh, okay. I see.
for example.
Okay, I see. Okay. I'm going to make a very brief remark on an enormous field here. So there is something called extended conformal field theory, which has been looked at by many people, including mathematicians. So the idea is that suppose that you have conformal invariance and you have this stress tensor, but you have other, say, currents, they're called currents, which are analytic functions, and all of that coexists. So if you have that, that is like having conformal symmetry and some other symmetry, and they are supposed to coexist. So that defines a more general class of conformal field theories, which has been investigated by a number of people.
I'm still totally baffled. Mu and nu range from 1 to 2, is that correct? Or from 0 to 1 or something?
Right.
What does z and z bar range over? Complex numbers?
Well,
how do you lower a 0 and 1 and get a complex number?
well, I mean, that's
Part is z and y is the imaginary part of z.
that's the definition of z and z bar, right? So I'm just trading my coordinates, my Cartesian coordinates, x1 and x2 for two other coordinates.
So
Z and z bar are just a different basis for the plane.
Just a different basis. I'm changing the basis, that's all. It's just that this basis here, z and z bar, has nicer properties than just the Cartesian basis for the plane.
well, they're not complex coordinates anymore, they're simply indices that indicate which coordinate you have.
Right.
Okay.
So you're lowering the subscripts and changing the basis.
Okay. And changing notation.
Right. Okay, there are some keywords about extended conformal field theories that you might have heard. So there is a superconformal field theory, parafermions, W algebras, Wessumino-Witten models. I don't know if those words are well known in mathematics, but that is sort of what people have been looking at. But okay, let's get back to my main point. Let capital X be any product of primary fields, and let C be a counterclockwise contour which encircles all the points where these fields are evaluated. And now I want to apply an infinitesimal conformal transformation, so Z prime is Z plus some small epsilon of Z. So I suppose that epsilon is small. I use the definition of the stress energy tensor, and what do I derive? Well, I derive that this contour integral here is equal to this. So here on the right-hand side you see the appearance of this conformal weight, and you see the coordinate transformation and its derivative. So that looks pretty nice, but what's going on? But it looks even nicer after you apply the Cauchy theorem. In which case,
sorry, is there any intuitive way of understanding that equation, the one that you've just finished talking about?
This one here.
Or I mean, I can't obviously. I've lost the thread of how you tie together the things that you've been talking about to arrive at that. Is it just a standard algebra, or is there more to do?
The only thing that is needed here is to apply the definition of the stress energy tensor. So that was the derivative of the partition function with respect to to the metric. To apply also that this correlation function here was defined as a functional integral with respect, which made the partition function appear, and then that these guys here are primary fields, so I know how they transform under such a transformation. So those three things put together after half a page of manipulations will give you this. So I'm sorry, it's sort of my basic line of approach. I'm telling you what goes into it, but not giving too much detail.
Right, so what you have is in transforming Z prime equals Z plus epsilon Z, that's defining a particular chain G mu nu.
Yes.
And you're carrying that through with the previous formula.
Exactly. Okay, so now I take this and apply the Cauchy theorem. And I remember what X is, and then I arrive at this. T of Z, one of the primary fields, becomes, I knew this was going to happen, because this thing here goes asleep, is equal to the primary field itself, times some pole and H, a pole of order 1, derivative of the primary field, and plus higher order terms. I like this equation here a lot. It's the first example of what we know as an operator product expansion. So the idea is, if you take two operators here, the stress energy tensor and a primary field, and if you approach the two of them, then you are going to generate singularities. So it tells you something about that variances, for example, of things may become pretty wild on small scales. And so seemingly here, this looks like some kind of approximation. So I would like to stress that this is not really supposed to be counted as an approximation. So An operator product expansion would be something like this, carried out to arbitrarily high order. So there's actually some ways of determining what comes after here. So, but I have left out the regular terms, keeping only the terms with poles. So it's supposed to be an exact identity provided that I write it out, and it's valid under expectation values. So actually one thing that you should notice carefully is that the stress energy tensor is kind of my litmus paper for finding out whether a field is primary. Because what I need to do is to make the operate product expansion and check that I get back the primary field with a pole of order 2, and then even as a byproduct I will get its conformal dimension. Okay?
Question?
Yes?
Sorry, I thought usually the word identity you do it by having a symmetry of the action, then you do change a variable in the functional integral and you arrive at an identity like that. But in the way you define, you don't talk about the action at all.
No, and that's a very good point. So one thing which is incredibly strong about conformal field theory is that I'll carry this lecture through all the way to the classification of the possible theories in 2 dimensions with conformal symmetry, conformal invariance, without ever writing down an energy or an action. So at no point I will define what the model really is that we are treating. I'll just postulate that it has this conformal symmetry, and then I'll find out all possible theories which satisfy that criterion. I find that pretty nice.
Another question. In the first formulation of conformal invariance, you had this transformation from x to x prime, and you had the multiplying factor which involves the scaling dimension.
Yes.
And then when you introduce the z and z prime, this breaks into 2 pieces.
Right.
How do you disentangle? How do you know which how to break it?
Yeah, you're anticipating on something that I'm going to say a little bit later on. So if you don't mind, I'll defer that question. Okay, what about the stress tensor itself? Is it a primary field? Well, no. Actually, it's not. It's quasi-primary, and it has conformal weight 2, but it's not primary. And so, while it's pretty easy to see that it has conformal weight 2 just from the very definition, I mean, because it was this functional derivative with respect to the metric, and we are in 2 dimensions, that's where the h equals 2 comes from, then there's actually no reason why the expectation value of t times t should vanish. So there will necessarily be a pole of order 4 with some coefficient that I'm going to call c over 2. And c is going to be very important later on. It's the central charge, also known as the conformal anomaly. And so that is some kind of Tolkien-like object, the master ring which governs everything. So it's the master critical exponent which determines what all the other critical exponents are going to be. And so roughly speaking, for a physicist, it measures the number of quantum degrees of freedom in the conformal field theory, whatever that means. Note that if c is equal to 0, then t would actually be primary. Okay, so what does t transform like then? If t is not primary, okay, suppose again that c is equal to 0, then here it's written the transformation law for a primary field of dimension 2, yes?
Can I ask a question? So in the previous slide, I thought I understood that t was some kind of operator value thing, because it sent a phi to some other field to some other field. Now you say t times t is actually in leading term a scalar.
It's a functional, right? It
You should
depends.
imagine angle brackets around that expression on the left-hand side. It's the expectation value of those things.
Oh yeah, okay,
You
of
should
course.
always
That.
ignore the expectation value brackets. You should imagine them everywhere.
Oh, okay. Okay.
It's just because somebody
You said it. You already said it.
somebody became lazy at some point.
No, that's fine.
They were supposed to put expectation brackets everywhere, but at some point they didn't want to, so they stopped writing them.
Thank you.
Okay, so if C is equal to 0, then you see here the transformation law of a primary field of conformal weight 2. Okay, so let's now just, to find out what the real transformation law is, let's just say that, okay, there's some extra piece here, which I'm going to call C over 12 times some object that I don't know what is. Okay, so that of course can always be done. It just remains to determine what this object is that I don't know what is. And so now to find out, I'm going to use that for projective transformations, this object must be 0, right? Because T was quasi-primary. So it was supposed to transform the way a primary field was, provided that you restrict yourself to projective transformations. And moreover, if I do 2 transformations, so I start with some z, then some z, I transform it into some w, and then I transform it into some w tilde, well, then this thing here had better be associative in the sense that if I do a 2-step transformation, or if I just do everything in a single go, that then I should get the same result. And after half a page of calculations, you find out that this object here is the Schwarzen derivative. Okay. So I know how T transforms. And actually there's a very nice side product that of this formula, which is obtained by just using the conformal transformation, which will take the plane into a strip of a given width L. And the end result will be that let's now talk in statistical mechanics terms, the free energy of a model on a strip of a finite width L will have some corrections to scaling in L, which will link to the central charge. So if I take the free energy per unit area for a strip of width L, then that is going to be the free energy for a strip of width infinity, so in the limit minus pi c over 6L squared plus higher order terms. So if you're doing numerical experiments, and if you want to find out what the central charge of an Ising model is, you define the Ising model on a cylinder with periodic boundary conditions, a cylinder of circumference L, and you do a finite size scaling analysis, and then you'll find out C from this result here, and C turns out to be 1/2. Okay, let me move to my next chapter here. Now I'm going to turn all of this into an operator formalism. Until now we were talking functional integration, and what I'm aiming at first and foremost is to obtain the so-called Virasoro algebra, and then I'm going to look at its representation theory. So if you want an operator formalism, you need to have what physicists would call a quantization scheme. That is to say, you want to say something about what goes on in your plane. So you should imagine that you are thinking in terms of an evolution operator or a transfer matrix which will construct the degrees of freedom of your plane gradually. So there is some specific way of moving through the system, and there is some evolution operator which gives you, so suppose that, let me try to draw this. So suppose, for example, that you have transformed your plane onto a strip, and suppose that you know the partition function for some part of the strip conditioned on what is going on here in the boundary, and then you want to add a little extra chunk. Well, then there's some operator which is doing that for you. So if I condition on what happens here, and if I sort of, in my functional integration, sum over everything which is going on in this extra piece that I'm going to add, well, then I get my partition function for the bigger system. And so the way of doing this is that I pick out some preferred direction for scanning through the two-dimensional system, and that is known as the time direction.
Well, in your setup so far, the metric has been Euclidean, or is it Lorentzian?
Until now, it has been Euclidean. Right.
And it's still Euclidean.
Yes.
Okay.
Okay, so there is some operator which I like to call exponential h, which propagates the system along the time direction, and the other direction is called space. Okay. Well, that's just because there's some analogy between statistical mechanics in 2 dimensions and quantum field theory in 1 dimension, where things evolve in time. So I'm just using some fancy names for the 2 directions. But so the question is now, what should I take for this h here? Well, I want to take h as the dilatation operator. So it's not at all going to look like this. It's going to look like I start at the origin. I have some chunk of my system, and then I'm going to add an extra annulus. So I'm sort of propagating outwards like that. Well, then you can convince yourself that the dilatation operators can be written like this. In terms of these ln here. So the ln are just the contour integrals of t, and they are known as Virasoro generators. Okay. Okay, I knew something about what happened when I multiplied t of z with t of z tilde. That was my operator product expansion. And now if I use a standard contour integration results on that, then I find out what algebra these L's here should satisfy. And the result is this. So this bracket here means commutator. So it's ln Lm minus Lm Ln is equal to this plus this term here, where the central charge appears, of course. Moreover, if I take L with L bar, then they actually commute. So that is the deep reason why we can focus on L only, at least for the moment. I'm going to contradict that 10 minutes from now, maybe, or maybe tomorrow. Because if I don't look at, if I take another geometry, if I take something like a torus and define my conformal field theory in a torus, then I'll find that the Ln and Ln bar will actually couple. And the way to find out how they couple is by imposing the requirement of modular invariance. Coming back to that.
Say that H is a dilatation operator. That means it satisfies some Schrödinger or heat-type equation involving the Euler type dilation. Why call that a dilatation operator?
Well, because what it does is to put a scaling transformation on your system.
So is there some Schrödinger-like equation saying d by d scale equals h something? E by D scale applied to something equals H applied to something?
Well, maybe I haven't really thought about that.
Worth a try.
So the thing fell asleep again. So let's wake it up. Okay, now I want to have these L's acting on some space. Okay, so this is going to be called a Hilbert space. So in a Hilbert space there is something called a vacuum, so a vacuum that is a state where nothing exists. And I will postulate that this vacuum, whatever it is invariant under projective transformations. It's easy to see that just as we have just seen that dilatations, or we have, well, seen, but not maybe proven, that dilatations were generated by L0, well then the projective transformations are generated by L plus minus 1, so I will just postulate that those annihilate this vacuum, and I will also postulate that L0 on the vacuum becomes 0. It's like fixing the ground state energy. So now what are the states of the Hilbert space? Well, the states are obtained by letting some primary field act on this vacuum. And I'm going to denote them H bar. I mean, just inside a Braun Ket like that. So H bar are the conformal weights, and this notation here means that it's a state in my Hilbert space. And then there is going to be something called a highest weight condition. So a primary field is annihilated if I act with it on it with some Ln, where n is a positive integer. And
I'm sorry.
okay, so that's
Does that define what it means for HH bar to be a highest weight
yes.
state? Okay. And HH bar doesn't depend on the choice of phi, only on any field with those conformal weights gives the same state?
I believe that I'm supposing here that there is only one field with those conformal weights. Otherwise, I would have to refine the notation a little bit.
I see.
Well, how many eigenstates does H have? Is there simply a single object, or are there many? Does H have one eigenstate, or does it have infinitely many? Or
Well, typically it's going to have just one.
so that means that if H is a scalar, only one. Oh, I see, one eigenstate.
No, I mean,
Number space is one dimension.
typically there is going to be only one primary field with a given set of conformal weights, H and H bar.
Well, does the phi on the right range over all possible conformal fields somehow?
So what I'm going to do here is that I'm going to do some representation theory. So you're going to see what the representation theory is going to be set up like. So maybe you can judge a little bit better in a few minutes. Okay? So I'm telling you how to organize this Hilbert space. So now I've got this highest weight condition. So I know that H is annihilated by Ln with n positive. That still leaves the opportunity of acting with Ln with n negative. So that defined what is called a descendant state. And a descendant state at level n bar is in general something like this. So I take my primary field and I act on it with a number of these operators, L with negative integers here as indices, both L bars and L's. Of course, by the commutation relations, I know how to commute these things through, so it doesn't matter if I put the L's first or the L bars second or the other way around. And also I might as well suppose that these integers here are ordered. Otherwise I'll just commute them so that they are ordered. So the sum of all the integers here is called the level. Okay? So I have some highest weight state up on top, and then I generate something which is called a conformal tower of states, which are descendant states. So this defines what is called a Verma module, or a highest weight representation. So that is to say one primary and all its descendants. And now I want to say something about representation theory. So the question is this module irreducible? And the answer in general is that it's not. So we have to do something to make it irreducible. But before doing that, let us just note that there's a very good reason for these descendant states to be called descendant, because their properties can be derived from that of the corresponding primary field. Suppose, for example, that you insert some descendant state in a correlation function. X, once again, X is a product of any number of primary fields. And now I'm going to put in an extra primary field and make it as descendant by acting on it with L minus n. Well, then you can actually show using the Watt identity that this is the same thing as the correlation function of the corresponding primary operator, on which I have to act with some differential operator, which looks exactly like this. So that is almost the same appearance that what you had in the Watt identity. So I never need to care about what correlation functions involving descendant fields are, as long as I know what correlation functions of the primary fields are. I can also write now the general form of an operator product expansion of two primary fields in all its glory. So what is going on here is that I take two primary fields. I can always conformally map the coordinates of one of them to the origin, of course. And that's going to expand on a sum of other primaries indexed by p. So they appear here, except that each primary is also coming along with all its descendants. So there's some coefficient here for telling with how much weight the primary p is appearing in this product. And then here's a sum over all these integer partitions which define the descendant states, including the trivial, including nothing. Some other coefficients, some weights here, some scale factors which are just dictated by scale invariance, and the descendant of the primary field P. Wow. These guys here are fundamental quantities. These guys here are easy to derive quantities, because everything that you need to do to derive these guys is to act on this equation by some ln with n positive, because then ln on this side here will start acting on this descendant field. Then I can use my commutation relations, and if I do that for all possible ln with positive n, then you can find out what these coefficients are. So these are easy coefficients. And these guys here are a little bit harder coefficients. And it turns out actually, well, it's kind of easy to see, I guess, just by multiplying both sides of this equation by a third primary field and taking expectation values and using the fact that you know what a 2-point function is and a 3-point function is by global conformal invariance. It's easy to see that these C1 through P are exactly the same coefficients that appeared in my 3-point function on one of the first slides. And now how can I find them? Well, I can find them using something which is called the conformal bootstrap method. So the idea is that instead of looking at 3-point functions, I should look at 4-point functions. And so any 3 points can be conformally transformed into trivial points in the complex plane, namely 0, 1, and infinity. So if I take a 4-point function, it's generically going to look something like this. And now what do I do? Well, now I take all possible limits of z going to infinity, z going to infinity, z going to 1, z going to 0. I use the operator product expansion to contract 2 of the fields and get just 1 single field. I write out what it means. And then I claim that this is just a function of z, right? So it should be the same function. Whatever the order of taking z to infinity first, or taking z to 1 first, or z to 0 first. And that gives me some consistency requirements. And these consistency requirements are actually enough to fix these coefficients here. So?
Input must be given somewhere. No?
Yes, the scaling dimensions of the fields.
Anyway, it's just a comment.
Yes?
Can a field be a descendant of 2 different primary fields, or are there kind of like direct sums?
No. No, they can't. At least not if I go to irreducible representations, and that I'm going to discuss shortly. Okay, so very little time remains. So I'm going to start the section on minimal models here. Here's the Hilbert space of the complete conformal field theory. It's a direct sum over the possible choices of conformal weights, some multiplicity n, and then Verma modules corresponding to the central charge and h, and on the other side the bar side. The multiplicities here can be fixed using modular invariants that I'm going to show tomorrow. And the definition of a minimal model is that this sum here is a finite sum. So there's a finite number of Verma modules in the theory. It's useful to introduce what is called the character of a module V. It's the trace of some formal parameter q to the power L0 minus c over 24. So everything here is well defined, except that you don't know what a trace is if you don't know what an inner product on the Verma module is. And that is defined simply by letting the conjugate of Ln be L minus n. And most of the time people like to write this small q, which you can imagine just being a formal parameter, as exponential 2 pi I tau, and taking tau in the complex plane and calling it the modular parameter. But anyway, what is going to happen here is that if a field here has some conformal weight h, then its corresponding character is going to start with a factor of q to the h minus c over 24, and then all the descendants are going to generate a series in this parameter q where you are just off by integer powers of q. So the character tells you how many descendants are there at a given level. Something that, of course, we would like to know. Now suppose that the world were a nice place to live in, and that the Verma module were already irreducible, then the number of descendants at level n would just be the number of integer partitions of the number n, right? Because, for example, if I want to be at level 3, I can produce descendants by acting with L minus 1, L minus 1, L minus 1, or L minus 2, L minus 1, or L minus 3. So there would be 3 of these guys equal to the number of integer partitions of the number. So the character would just be q to the h minus 0.24 divided by p of q, where p of q is this generating function of integer partitions, which I can write in this way. Note eta here is the Dedekind eta function. And p of n is the number of partitions that I already said. Well, that unfortunately is not the case. Most of the time, there are such nasty objects around as null fields. I have to stop very shortly, but this is not the place to stop, so I will just permit myself to take 3 minutes more. Sorry about that. So a null field is a linear combination of descendants at some fixed level. Okay? So suppose we are at level 2, for example, then a null field will have this form for some parameters a and b. And by definition, a null field is both descendant and primary. So of course it's descendant, that's what I wrote here. So the key definition is that it's also primary, so it's annihilated by all Ln with positive n. That can happen only for very special values of h, the conformal weight of the primary field. So, since it's primary, it has its own Verma module, right? And that Verma module is a proper subset of the complete Verma module of the primary field. But the two Verma modules are orthogonal, using the inner product because of this. And so in particular, everything in the Verma module generated by chi is orthogonal to itself, so the norm of the state chi is 0. Okay, so think of probability theory. You don't want to have anything which has probability 0 anyway. I mean, you might as well throw it out. Of course, you could keep it, but if you throw it out, things run the risk of being simpler. So let's try to get rid of this null field. Actually, let's try to obtain an irreducible module, which I'll call M, from the Verma module C by simply setting chi equals 0. So I'll quotient out the null fields. So I have to think a little bit. If you just allow me to take this transparency, then I'm at a main conclusion, and then I'll leave you for your coffee. Okay? Okay, so now what we want to do actually is to construct unitary representations of the Virasoro algebra. What do I mean by unitary? Unitary means that there is no state of negative norm. So clearly the fact that these null fields had 0 norm, that means that somehow if I push things a little further, things might start to get a negative norm. Okay. So the first step in this construction here, which I'll only sketch, is to compute the so-called Katz's determinant of inner product between all descendants at level n, some given level. So in this case here, over here, I would get a 2x2 matrix. And I try to find its root. And of course, that's a difficult task to compute that, but the end result is that things become simple. If I choose this parameterization of the central chart C and of the conformal weight H, so it's a parameterization which makes use of some M, and some R and some S. R and S are integers, and their product is less than capital N. And in a very famous paper by Frieden, Q, and sorry, typo, I think Schenker, this R should be an N. They find the unitarity condition for conformal field theories with central charge less than 1. It is simply that all of these guys here are integers. M is larger than or equal to 2. R is in between 1 and M, and S is between 1 and M included. And so once you have that, you would like to see what the central charge are when you put M equals 2, 3, 4, and so on. So you find out that M equals 3 corresponds to the Ising model. It gives you C equals 1/2. And lo and behold, these H's here are going to be the critical exponents of the Ising model. So this result here is very strong. So that was for M equals 3. If you take M equals 4, then you get the tricritical Ising model. So where you have vacancies in your Ising model. If you take the next following value, then you get the 3-state Potts model. And the next one again is the tricritical 3-state Potts model. And so on and so forth. So without ever saying what the energy functional of any of these nice statistical physics models were, you have deduced here all of their critical exponents. And so this is a nice place to stop. And there's a question.
Yes, how can you tell it's the Ising model and not something else?
Well, I think I made a transparency on that later on. But anyway, I mean, you can try doing this for your Ising model. You can try computing what its free energy on a cylinder is to try to get C, right? So of course, I mean, back in 1984, 85, 86, there was a hectic activity of trying to identify some of the well-known models, for some of which people had exact solutions with this classification. And the way you go is that you either derive by other methods one critical exponent exactly, or you do some numerics to find C just from a numerical transfer matrix diagonalization or something else.
But for the Ising, this finite size F there is also an exact formula for it?
For this one here, you mean for the remaining terms here?
No, for the FL.
Well, the Ising model you can solve, right?
Since time is short, maybe we
right.
can
So
have
yeah,
our
maybe we should stop here.
Thanks very much.
So are the hierarchies on the web already?
No, not yet.